Hey everyone, it's Justin again. Now that we know how to graph and solve systems of inequalities, we can give them some context. So in this video, we're going to be working through word problems involving systems of inequalities. It takes 12 people to assemble a car for $5,000 and 15 to assemble a truck for $10,000. The manufacturing plant has 180 employees and a budget of $100,000 for the week. How many vehicles can be made? In this problem, we've got a bunch of information all mixed together, but there are two major factors affecting how many vehicles can be made: the number of employees and the budget. Each car takes 12 employees and each truck takes 15. But the total amount of employees used can't exceed 180. In other words, the amount of employees building vehicles has to be less than or equal to 180. For the budget, it costs $5,000 to assemble a car and $10,000 to assemble a truck. And the combined amount spent to assemble vehicles can go as high as $100,000, but no more. Now that we've got our inequalities figured out, let's solve them. The easiest way to solve a system of inequalities is by changing the c's to x's and the t's to y's, and then graphing the system. Both inequalities here are in standard form, so graphing is going to be easy. Find the intercepts of the first inequality, and when we plug in the test point 0, 0, we find that it is a solution. Which makes sense, because if we assemble 0 cars and 0 trucks, we're definitely going to need less than 180 employees. For the second inequality, we graph the intercepts and then shade. Instead of actually testing the point 0, 0, we can remember the context of the inequality. If we assemble 0 cars and 0 trucks, it will certainly cost much less than $100,000. So 0, 0 is a valid solution. Remember, you aren't even required to use the point 0, 0. You can use any point that makes sense to you as long as it isn't on the line. If you instead chose to test using this point, 1, 2, then you'd have to ask yourself, would that fit the problem? And it would, because assembling 1 car and 2 trucks would cost a total of $25,000, which is still below the budget of $100,000. So now that we have the graph and we can see where the overlap is, how would we answer the question, how many vehicles can be made? We assume that the manufacturing plant wants to make as much profit as possible, so they're going to make as many vehicles as they can. 2 cars and 3 trucks is technically a correct solution, but realistically, they're going to make more than that if they can. So what are some realistic answers? Well, they might choose to use most of their employees for assembling trucks, so maybe they'll make only 1 car and 9 trucks. Or maybe they'll put most of their workforce on car duty and make 13 cars and 1 truck. Or maybe they want to make about the same amount of each, so they go with 6 cars and 7 trucks. Since that point is on the solid line being overlapped, it is as valid as an answer as the other ones. Especially with real-world scenarios, more information is better. If we had an inequality for how much profit we wanted to make, we could restrict the solution area even more and find even better answers. Next up, a furniture store sells sofas for $200 and recliners for $100. The shipment trucks have 140 square feet of space, of which sofas take 21 square feet and recliners take 9 square feet. If the store wants to make over $1,600, how many of each item should they have shipped from the warehouse? We've got enough information here for 2 inequalities, shipment and profit. First, for the shipment, sofas take up 21 square feet and recliners take 9. There is a maximum of 140 square feet available on the shipment truck, so the sofas and recliners can only go up to that much, no more. For the profit, the sofas bring in $200 and the recliners bring in $100. The store wants to make more than $1,600 in sales. More than, not or equal to. So we've got a system set up. All that's left is to change the variables to x and y, then graph the system and find some possible solutions. We graph the first inequality by plotting a solid line through its intercepts. To shade, remember that this inequality represents space on the truck. Would there be enough room on the truck for 0 sofas and 0 recliners? Of course. Let's do the same thing for the second inequality. We draw a dashed line this time through its intercepts. Then we figure out which side to shade. If the store sells 0 sofas and 0 recliners, will they make over $1,600? No, they wouldn't make any money, so 0, 0 is not on the side with the solutions. The solutions will be in the overlapping area, which is where? We could see from the direction of the lines that if we move further to the left, we'll finally see some overlap. But that's in the negative x values, which doesn't make sense in this problem because we can't ship or sell a negative amount of furniture. So we have to stay in the positive values where there is no overlap. So what's the solution? You probably figured it out already, but there isn't a solution here. Any amount of furniture that will fit on the shipment truck won't make enough profit. And any amount of furniture that will make the desired profit will be too much to fit on the shipment truck. This big gap between the shaded areas shows us that there simply isn't an amount of sofas and recliners that will all fit on the truck and make more than $1,600. The store will need to renegotiate how much money it wants to make or find a bigger truck. That's all there is to it. Set up the system using the given information, graph it, and find the solutions if the situation even has a possible solution. Practice makes perfect, so don't forget to play the practice game on our website. See you later.